the wavelength of the 88D. So I say it's been rated 88D. Some material may be inappropriate for a wavelength under 10 centimeters. All right, that's corny joke number one out of the way. There's a few more coming. I apologize in advance. Looking at reflectivity, we know it, we love it, we're used to seeing it. There's our typical scale. Of course, we can have negative values. I'm just showing a range of more common values here. What is it telling us off the top? Well, how much stuff is there? Just how much precipitation, non-meteorological echoes, just how much is out there? How big is it? Bigger items tend to scatter more than smaller items. Let's say a big hailstone is going to scatter more than a smaller snowflake, for instance. How reflective is it? That's really important too. Liquid actually is more reflective. Liquid water is more reflective than ice is due to the density of water being greater than ice. And so that's why you see something like bright banding, for instance. And we'll talk about bright banding here in a little bit and how you can spot the melting layer with more confidence. So when we're dealing with our typical distribution of hydrometeors on the warm season convective side, hail generally tends to be 60 plus, and then decreasing intensities of rain from there. Not to say these are hard and fast rules, but in general. And then looking at the winter side of things, what we care about, especially today, wet, dense, heavy snow, you can see it's not out of the question, 40 to 50 dBz. If you have really heavy, really dense, really wet snow that's maybe just about to start melting, it's not out of the question. A fluffier, drier, heavy snow is more 30 dBz, for instance, and then from there, light to moderate snow. All right, so now the dual-pol variables. Let's talk about those. Differential reflectivity. Some typical values in the scale, maybe not so much down here in the negatives, but especially once you get to about 0 dB plus. What is it telling us? A big tool that we gain from ZDR is, what is the shape of the precipitation particles? Are they wider than they are tall? Are they taller than they are wide? Are they spherical? We can start to back out some information about hydrometeors with the shape. How are they oriented? Are they tilted in one direction? Are they canted? That's a sort of a fancy word for tilted in another direction. We get a lot of information there too. So graphically, what is it? What is it doing? Well, we imagine some bigger raindrops, and of course these aren't all exactly to scale, but let's imagine some larger raindrops. They tend to be wider than they are tall, just the way surface tension of the raindrops work as they're falling, other things, aerodynamic effects. They make these what's called oblate spheroid shaped hamburger buns is what I like to call them, because that's what they start to look like. Melting hailstones have more horizontal component typically than vertical component, and newly generating dendrites or even plate ice crystals, plate-like ice crystals, they may have more horizontal than vertical component, as you see with these two arrows. Things that scatter back more energy in the horizontal than the vertical have higher differential reflectivity. They have higher ZDR, so 2, 3 plus dB. Basically, when you think positive values of ZDR, you want to think more width than there is height, or more in the horizontal than there is in the vertical. All right, let's introduce some spherical objects. Smaller raindrops, droplets, dry hailstones, clumps of dendrites, clumps of snow crystals, what we call aggregates. The way they appear to the radar, and there are a few things going on in the EM world behind it too, the electromagnetic world behind it as well, but we won't go into those details. But in general, the way these all appear to the radar, especially these smaller drops, is very spherical. You get equal amounts of power back in the horizontal and the vertical. So you tend to get ZDR values close to 0. So if you're getting values close to 0, you want to think more spherical. And then if you were to get negative values, you actually think more in the vertical than the horizontal. So you can see how ZDR gives us an idea of the shape of the hydrometeors we're dealing with. All right, moving on to correlation coefficient. There's our general scale. It is unitless since we're dealing with a correlation value here, but typically you're going to see values anywhere from 0.3 up to 1, with most of your meteorological scatters being up top. And what is it telling us? How diverse are the precip types in the radar sample? Is it all the same hydrometeor? Is it all the same phase? Or we have a bunch of mixture of ice and liquid? We have a bunch of different things going on. Are there non-meteorological echoes? That's a huge use with correlation coefficient. Those tend to drive those values down, as you'll see here in a second. Pure rain or snow tends to be pretty high, 0.96, 0.97 and higher. Melting snow or hail, which of course we'll be interested with when we're dealing with melting in winter weather, you start to get more of these yellows if you're dealing with the typical sort of packaged color curve that a lot of people use when looking at the correlation coefficient. These values that are 0.9 or 0.95, 0.9, and perhaps even lower. Giant hailstones, not really a concern for today, but just for reference, tend to drive values even lower. You can have values 0.85, 0.8. They get these weird shapes, and they also do some funky things with the scattering process back to the radar that causes a drop-off in correlation coefficient. And non-meteorological scatters, tornadic debris, bugs, friendly barn swallow, for instance, they will drive values typically even lower, where you get into these blues, 0.6, even lower than that. All right, specific differential phase, and we are going to use this today in an example in one of the operational applications later. So that's why I wanted to introduce it, and it's one that's probably the least intuitive out of the dual pole variables. At least what I've gauged from some people is like, I don't know how to use it. I mean, I know it involves a lot of liquid water, and we'll talk about that, but what does it actually mean? Hopefully I can help clear that up for you. It's measured in something known as degrees per kilometer, and we're not talking about degrees in the sense of a temperature. We're talking about degrees in the sense of how far along a wave. If you imagine the trough and the ridge of a wave, or the trough and the crest of a wave, are you talking 180 degrees, 360 degrees? That's what we mean in terms of degrees there. How far are we along in terms of a wave? And so it's measured in something called degrees per kilometer, and I'll describe what that means here in just a second. But what you want to know is how much liquid water is present, or what it tells you, how much liquid water is present. That's one of the biggest tools behind KDP. Another thing, and what we're really going to drive home later, is how well are snow crystals growing aloft. It's very subtle, but you can back out a lot of really useful information when you look up top at where you have your favored crystal generation regions. You can get a lot of information from KDP, and so we'll talk about that here in just a little bit. Lots of melting hail, you tend to get very high values of KDP, 5, 6 degrees per kilometer. You get smaller than that when you start to deal with liquid, just moderate to heavy rain. You can get values that are a little bit lower, more in the range of perhaps 2 to 3 degrees per kilometer. You will want to think, though, the more liquid there is, the higher values you're going to get. And then what we were especially interested in is crystal growth aloft. It's a very narrow range typically you see when you're dealing with ice crystal generation aloft, but even subtle changes where you go from maybe 0 or 0.1 to 0.5 can be a big difference. And so we'll describe that later when we get into our little heavy snow section of this presentation. All right, so I just sort of told you what values you can tend to see with different hydrometeors, but what does it mean physically? What is going on with KDP? The better you understand the process behind it, the better you can use it to understand how a winter storm, for instance, is changing. So let's imagine a group of raindrops here, and they're bigger raindrops, so they have more liquid in the horizontal than the vertical. And we send our two waves at them, our two polarizations, I should say, at this group of raindrops. So we have our vertical in the yellow or horizontal in the blue. As you can see with these raindrops, because they're wider than they are tall, the horizontal wave is going to just run into more stuff than the vertical wave is. It's going to encounter more liquid than the vertical wave. So imagine, you know, you're in a race with somebody in a car, or they're in another car, and they're on pavement and you're in mud. Of course, they're going to travel faster than you are. It's not a very fair race because they don't have to go through mud at all, or maybe just a little bit of dirt on the road versus you going through all this dirt, all this mud. That's all that's going on here, is that horizontal wave is encountering more stuff. So what do you think is going to happen to it? Well, it's going to slow down relative to the vertical wave. So what specific differential phase is telling us is how much that horizontal wave is slowing relative to the vertical wave. If neither of them are slowing relative to one another, or slowing down relative to the other, you get 0 degrees per kilometer. So that degrees is how much of the wave, for instance, is starting to lag behind the other wave. And we measure it in over the course of a kilometer, how much is that lag building? So if you imagine a lot of raindrops, a lot of liquid water, that horizontal wave is going to slow a lot relative to the vertical wave, and thus you're going to get very high values of KDP. And so you can see where it helps to tell you how much liquid water is present. Similarly, if you have a lot of crystals generating aloft in your, let's say, your dendritic growth zone, you have a lot of these horizontally oriented dendrites that are slowly falling. And while they're not as dense as raindrops, and so they're not going to cause as big of an increase in KDP, you still have that same process ongoing. And you can see how you get KDP to boost. And so you can start to use this to tell you an idea of, A, how much is growing up there, and B, are they these crystals that are really efficient and giving me high snow to liquid ratios, things we care about to make a forecast. So we'll talk about that later. All right, so that's our cover of the variables we're going to be using today. Each variable is a puzzle piece. The more you consider, you can put a better picture together, just like a puzzle. If you put more in there, you're going to get a better picture of what's going on. But with any of this, you always want to make sure you ask yourself, does your diagnosis make sense? If you're looking at dual-pol data and you say, well, this looks like heavy snow, but it's 60 degrees at the ground, you probably don't want to be putting out a winter storm warning, for instance, for heavy snow. Of course, that's an extreme example I'm giving you, but I'm just driving home the point that you always want to make sure that what you're diagnosing with the radar fits in with everything else, your mesoscale analysis, and your conceptual idea for the day of how a winter storm might be evolving. Okay, let's breeze things over. Let's get into winter weather applications. That's what we want to do. Batman and Robin, one of the greatest Batman series. I'm obviously kidding a little bit with that, but Mr. Freeze gives us a great amount of one-liners for winter weather presentations. So as we move forward, let's talk about the melting layer signature. It's the most common signature we can see in winter weather, really any time of year, but we want to essentially start with our foundation and build up from there. So let's use the tools of the trade to help you spot bright banding with more confidence. We just talked about correlation coefficient, but to drive home one more time, tells us how diverse are the precip types in the radar sample. Is there a mixture, melting for instance? Pure rain or snow, very high, and you drop down as you get more diversity. So melting snow or even melting hail, so any sort of melting process, you get a diversity in your resolution volume with the radar, and thus you drive down correlation coefficient values. Differential reflectivity as well gives us an idea of the shape of the precipitation particles and how they're oriented. So remember this melting hailstone right here, or even if you had, let's say, the snow that starts to melt, it might drive ZDR up even further, because what it does is the liquid tends to collect around the horizontal axis as this melting is underway. And so you get more power back in the horizontal than the vertical, and that drives ZDR values up as well. So you want to think melting, lower CC, diversity. You want to think higher ZDR because we're getting more liquid, and it especially likes to collect around the horizontal axis, so that drives those values of ZDR up. More spherical objects, once again, closer to about 0 dB because you have those equal contributions in the horizontal and the vertical axes. So spotting the melting layer. Let's imagine here we have our warm air that extends down to the surface. There's some point at which, once you go high enough, though, you drop below 0 degrees Celsius, so your snow melts, turns into raindrops, and our radar scans our domain as it goes around, and we get sort of this nice, clear ring shape in our melting layer, because at the same spot, our radar beam, if we assume a nice uniform distribution across our domain, our radar beam is traveling through the melting layer. So we get this ring-type signature with the melting layer. If you imagine sort of looking up at least at what reflectivity would look like, or we're looking down, however you'd be looking at your radar image from your perspective, you get this ring. So there's that ring where the radar beam is passing through the melting layer in reflectivity, and what's going on is water is collecting on these frozen particles, perhaps frozen snow. And so the structure of the snow, though, is still somewhat intact. So it's still a larger hydrometeor, but then it's collecting water. Water tends to send back more power than ice does. And so to the radar, it looks like a huge raindrop, and that's why you get the bright band to occur. Similarly, correlation coefficient, like we talked about, you see this ring-type structure where the beam travels through the melting layer. You get this decrease in correlation coefficient because through the melting layer, you have a diversity of hydrometeors. You have some ice, you have some liquid, you have some liquid on ice. There's a whole mixture of things going on there. So let's get into an example. How can we use it? How can I use the melting layer, not just to say, well, okay, we have rain at the surface, I'm going to go home for the day, but maybe to predict a change in precipitation type at the surface. This is an example from a few years ago from Burlington, Vermont. And on the left is reflectivity, on the right is correlation coefficient. And all my radar examples coming up, on the left-hand side, you'll see the elevation angle of the image, so what elevation angle the radar is pointed at, and then the time, and then in the upper right, you'll see the date if you ever want to go back and look at one of these cases individually and grab the data. So on the left here is reflectivity, on the right is correlation coefficient. We see a nice, clear, bright band melting layer signature, and there is our signature and correlation coefficient where we see a very clear drop-off in CC value. So we know we have this complete melting going on aloft. We'll highlight it right there for you. And now here's a loop, and we're going to go forward in time. You'll see what happens with our melting layer. It contracts in towards the radar. So what do you think is going on there? If we have this contraction of the bright band, we have this contraction of lower CC values coming in closer to the radar. Well, it means your melting layer uniformly across the domain is descending towards the ground. And what was going on is we had a deeper layer of cold air advection, bringing in colder temperatures, and so melting was getting closer and closer to the ground. The melting process wasn't starting until closer and closer to the ground. So if you're sitting in Burlington and watching this going on, you're thinking, we may be about to switch over to snow here pretty shortly. We'll do it with DDR, and this is a little grainy or noisy. We're dealing with level 2 data here, and it's not smooth, so you have to bear with me, at least in this image. But you can see the same idea. Here's that higher ring of ZDR, and then watch as it contracts in towards the radar. That's another indication of that melting coming in closer to the radar. And what we saw was surface reports show that Burlington switched over to snow over the next hour. So if you had a forecast and you think maybe a few hours from now, the thermal profile, at least in the model, or let's say you're looking at the RAF or the HER, or however you've had it figured out, you expect snow to, or rain to switch over to snow within the next 2 to 3 hours, and then suddenly you see this ring contracting into the radar really quickly. You can use that to say, the radar is giving me a lot of confidence that actually this changeover is going to be occurring a lot sooner. And so you can use that ability in just the evolution of the bright band and adding confidence with the dual-pol variable to help you deliver that nearcast that much better. So the melting layer signature. Dual-pol data can confirm the location of the melting layer. No longer do we just have to depend on higher areas of reflectivity to give you an idea. And of course, right there, I give you a pretty clear example of a bright band signature. So even without the dual-pol variables, you could probably say, yeah, that's a bright band ongoing. There are a lot of instances, though, where it maybe isn't quite as clear. Perhaps only across part of your region do you have melting ongoing. That's where dual-pol data can come in really handy to help you out. You want to look for those lower values of CC, generally less than about 0.95, and increased ZDR values in a ring shape, with a ring shape being, in the case of a uniform melting layer across your domain. And higher radar tilts, it's always important to stress, look up sometimes. Look up from that 0.5. You can get a clearer view of melting layer height and the evolution when you take some of those higher tilts and sort of clear yourself of the clutter and get a nice slice really through a melting layer signature, for instance. Okay, so now let's get into the really interesting stuff. This is the nitty-gritty where you can really see dual-pol shine and how it helps us with our capabilities. So transition zones and refreezing. When I say refreezing, I mean transitions into sleet pellets. So freezing into ice pellets again. So don't fear the wintry mix. We can use a unique melting layer signature to help us out. How do we do that? So we had our standard melting layer before, uniform distribution across our domain, and our radar scans around in a circle, and we get that nice ring shape that we were seeing before in our previous example. All right, so what happens then if we have a partial melting layer? Over only part of our region do we have temperatures or a thermal layer moving in that has temperatures above 0 degrees Celsius or 32 degrees Fahrenheit. So let's imagine we have snow falling over our radar. Our radar is nicely entrenched in a snow regime. We have melting ongoing farther. Let's imagine to the right is to the south. So to the south of the radar, we have melting ongoing. Our snow falls into this warm nose aloft. It melts completely and then falls back down to the surface. It doesn't refreeze anywhere in here, so right in this zone we might expect freezing rain, for instance, where our surface temperatures are once again cold enough for frozen or freezing precipitation. But right in the middle, what do we have going on? Well, we get some of that melting again, but we're right on the edge of our warm nose. Temperatures aren't necessarily that warm. They may be just above or right around 0 degrees Celsius. So we get this sort of partial melting. We don't get this complete melting of hydrometeors ongoing. Additionally, what also happens is the melting process itself, like evaporation, is a cooling process. You have heat going into the hydrometeor to help melt it, and so you can locally cool the environment, especially in heavy precipitation, and so that also causes this sort of incomplete melting right on the edge of the warm nose, right on the edge of a melting layer, perhaps moving in to your area. So now suddenly what you have going on is hydrometeors that are not melting completely. So maybe there's a little bit of liquid on a snowflake or some branch structure. You then introduce that hydrometeor into colder air closer to the ground that is back below freezing. And those particles are now way more efficient at refreezing into sleet pellets because they have that internal ice structure still intact in them. So you tend to see refreezing right there on the edge of the warm nose. And what you get is this zone, essentially, of melting / mixed phase. When I say mixed phase, you're talking about ice and liquid together. And you get this interesting descent of the melting layer right on the edge of that warm nose. If we refer to the warm nose as our area that happens to be above 0 degrees Celsius, that's what, when I say the warm nose through this presentation, that's what I'll be referring to. So right on the edge of that, you get a descent of the melting layer and a descent of this mixed phase regime. And we can use that descent with our radar data to really give us a great idea of where we're seeing a change in hydrometeors at the surface, where we're seeing a transition from snow to sleet and then freezing rain. All right, so this little inset here is correlation coefficient from a case in Long Island that I happen to be there for. I used to work at the New York office up there on Long Island, and this was a big snowstorm we had up there. And you can see this interesting sort of half ring shape in low CC values with this connection in the middle. So imagine along this dashed line is our radar beam traveling out, and it slowly rises in elevation or above ground level as it travels away from the radar. So let's break this down one by one, what we're talking about and how we can use this information. So region 1 is pure snow. We haven't passed underneath the melting layer yet or through the melting layer. So the snow is making it all the way to the surface, and right near the radar, we have very high correlation coefficient because we are dealing with a purity in our resolution volume. We're dealing with all snow, and so it gives us nice high CC. So that's great. All right, 2 is now where we're passing through that descent that I was talking about before of the melting layer, and you see this a lot. I've seen it over pretty much a large chunk of the CONUS, and so it's not. I have an example from Long Island, but I've seen it from radars all around the country, so this applies pretty much everywhere from what I've seen. So 2, this descent of the melting layer, suddenly our beam is traversing a region where we have a mixture in phase because we've had our melting layer drop down towards the ground. Recall that a mixture in phase sends correlation coefficient down. When we send it down right in here, when we pass through this region, I should say, we send our CC values down, and that's what we get, this little line right in here sort of connecting this half ring type shape. We go to 3 now, and you'll notice CC goes back up. Well, that's interesting. How's it doing that? Well, we're now passing through this area of small drops or raindrops that are underneath the melting layer. We've moved through the area where our melting layer is descending towards the ground. We're now underneath the melting layer, so we've had complete melting into liquid drops. And because there's a purity, once again, in the resolution volume, there's little diversity in our hydrometeors. We send our CC values back up, so we get higher values of CC. And then 4 is where we actually pass through the initial melting layer that is associated with that warmer air moving in aloft. So that's, if you imagine our previous example where we had the full-on melting layer ring, the full ring, this is sort of a half ring, and that's where we're passing back into the melting layer. We have that diversity in hydrometeors, and we're seeing that drop-off in CC values. So you can break down with this half ring type structure and this connection how you start to pick out the different hydrometeors at beam height within this half ring signature. So here's that example from Long Island, New York, and KOKX is the radar. Reflectivity, there's probably some bright banding going on here. There's some really high values of reflectivity, but man, it's tough to get detail on what's going on where. So we want to get more details to diagnose winter precip. Let's look at correlation coefficient. We see a lot of what appears to be melting going on to the south of the radar, but then there is that connector, I like to call it, between the ends of the ring. What we have is heavy snow in the high CC values. If you were to tilt up, you'd see high CC values going all the way aloft. And then in this line connecting the ends of the ring, you tend to see heavy sleet there because remember, that's where you have the descent of the melting layer. And that descent helps bring those embedded ice cores inside that initially melting hydrometeor into a sub-freezing layer once again, and you tend to get sleet there. And sure enough, at this time, reports on the South Shore of Long Island indicated we were getting a lot of heavy sleet. And so you tend to see sleet right underneath where you get that descent signature in the melting layer. And then farther south, you see liquid reaching the surface. In this case, heavy rain. Of course, it was out over the ocean, so you know, it's just a lot of rain into the ocean. But let's say it were over land, you'd be very concerned then, what are the temperatures near the ground? What are the surface temps? Because perhaps it's heavy rain, perhaps it's heavy freezing rain, if temperatures or surface conditions or just elevated surfaces maybe are below freezing. Let's take a quick cross-section through this to give you another idea of it. And here we'll go to the cross-section, reflectivity on top, correlation coefficient down on bottom. So there's snow right near the radar. CC is plenty high all the way down to the surface. Then you see this descent of the melting layer. There's the melting layer right there where I got my cursor, and then you can see where it comes to the ground. So we transition to sleet, and the reports, the MPing reports we got, the ASOS reports, all were indicating that we had heavy sleet there ongoing. And then farther south, where you're no longer seeing that descent of the melting layer, we know we have complete melting. And so this is where we'd be concerned about rain or freezing rain, depending upon our surface temperatures. Here's one more example moving down the coast from a different case. This is from DIX, the Philly or Mount Holly radar, reflectivity on the left, correlation coefficient on the right at 1.4 degrees. And I'll highlight right here, you can see more of that idea where I've highlighted it there sort of in that black, but I'll go back and you can see that we have this descent of the melting layer connecting the ends of it. So this is where we'd be expecting a sleet potential, and sure enough, reports indicated that we had sleet there. And the cool thing that I'll highlight real fast is you can see some of the really amazing impacts that even, let's say, a little gravity wave, some wave may have on the melting layer. Look at how you go from some descent to no descent to some descent. You can see how subtle some of these influences are on how the melting layer perhaps oscillates, perhaps how it impacts our surface precipitation types. It's really amazing when you start to see some of these details that you can pick out. All right, so here's a case from Wakefield as we move farther down the coast, and you say, I don't see any descent. It's a nice clear ring. No melting layer descent, no problem, right? I don't have to deal with sleet. It's either rain or freezing rain. I got this. Well, not exactly. So we showed you before where we had that descent of the melting layer. Let's say we don't have it, but what we do have is this uniform warm layer aloft, but then we have sub-freezing temperatures back close to the surface. And if that cold air is deep enough, we can refreeze even if we don't have some embedded ice core in our liquid drops as they clear the melting layer. If it's cold enough and it's deep enough, we can get refreezing into sleet. So what goes on in this case is we get that initial melting layer ring aloft where we see that diversity in hydrometeors, but then we get this much more subtle ring that appears, believe it or not, in our area where we change over to sleet when we're looking at our radar. So what is that signature and how does it work? We go back to our image here, but in this case we have ZDR on the right and we have reflectivity on the left still. And we're looking at 2.5 degrees. Remember, it helps to look up sometimes at to give us a clearer view of what's going on aloft and then to help us get a better idea of what's making it to the surface. And you'll see it flash right there sort of subtly, and I'll highlight this ring that you see here. And you notice there's a change, this clear change in our radar image, and it's this nice circular area. You see this very slight drop in reflectivity, and you see this increase in ZDR. Well, that drop in reflectivity, it tends to be around 7 dBz, the way the scattering works, but it's due to the lower density of ice. As we go from liquid to ice once again, ice doesn't like to scatter as much back to the radar, and so we get this drop-off in reflectivity. Well, something's going on at this level if we were to sample it with our cursor, for instance, maybe in AWEBs. Well, why does ZDR go up? That's kind of weird. And what's actually going on, or what's suspected, is when you're refreezing into sleet pellets, you tend to see the smallest drops freeze first, and so that leaves you with a distribution that's skewed towards bigger drops. And you remember when you have bigger drops, they tend to have more horizontal component than vertical component. What does that do to ZDR? Well, that drives ZDR slightly upwards. We're not dealing with huge drops, but we're dealing with slightly bigger drops because the smallest ones are freezing first, and that helps to drive ZDR up. So you can see this very subtle signature, but it's definitely there, and that's a very clear sign of refreezing going on. So transition zones. Partial melting rings indicate a transition zone across the region. You can use that partial ring to tell you that some change in p-types at the surface is going to occur if it's moving about your domain. connecting the ends of that partial ring, occasionally you see a line of lower CC. If you see it, often that's where we witness sleet at the surface, because you're getting that descent of the melting layer, and that makes the conditions for your hydrometeor to refreeze into a sleet pellet that much more favorable. So if you see that little connector line, you want to think sleet right there. And so if you see it moving somewhere, you want to think there's going to be a transition to sleet wherever it's moving to. The lack of such a descent, that descent line in CC, means that freezing rain or rain, complete liquid, is much more likely at the surface. But as we just saw with that previous example, you want to watch out for low-level refreezing into sleet pellets. And that's where it helps, like we talked about off the top, having a complete idea, or at least doing your homework before getting into the radar analysis of what is the thermal profile from an observed sounding, from forecast soundings, from surface conditions, from soundings from aircraft, whatever you have, what is it telling you? What are you expecting to occur with your P-types? Then toss in the radar information to help confirm or maybe lower confidence with what you were expecting. Okay, heavy snow identification. Tell the difference between heavy snow and really heavy snow. And this is where we're going to use KDP more to help us out with that. So we're looking for two features when it comes to heavy snow. You want to see lots of crystals, of course, growing aloft in our favored regions, that's sort of -12 to -18 degrees Celsius, somewhere in there, where you get that efficient growth of dendrites or even perhaps some plate-like crystals. And then you also want to see aggregation, that clumping of these crystals into big fluffy snowflakes, because suddenly now they get very fluffy, they stack up even faster, that increases your rates as well. Specific differential phase. We're going to be using it as we go forward in this little module or subset of the presentation. And so we focus right in here on these lower values of KDP. 0 degrees to 1 degrees per kilometer, thereabout. It's a very narrow range, so sometimes perhaps if you want a color curve or you develop your own color curve that you could use for snow situations to help highlight some of these values, but what you want to know is it's a subtle range, but increases in this small range of KDP can mean big things for how many crystals are growing aloft, because as we get more of that horizontal than the vertical and more stuff, more ice in the horizontal than the vertical, we get those higher values of KDP. So crystal growth. Let's imagine we're looking up in a cloud. We have this big gray mass of a cloud in my slide example here. And you're looking around -12 to -18 degrees Celsius. So we're focused in on what we might describe as our dendritic growth zone. And we can even say we have some plates growing in there as well, perhaps even some colder temperatures, -19, -20 degrees Celsius. But we're getting lots of these horizontally oriented crystals developing up there. And there we send in our wave again. In the yellow, we have our vertical polarization. In the blue, we have our horizontal polarization. And just like we talked about before, the horizontal wave will run into more stuff than the vertical wave. It's going through tougher running drills than the vertical wave is, for instance. And so it's going to slow down relative to the vertical wave. Remember what that does to KDP. It boosts KDP. In this case, a little bit, subtly. So a greater number of these crystals drives KDP up. Typically, this is what I've seen, and this is about what some research has shown, but these aren't hard and fast rules. There's a little bit of variability to them. So I'm going to say you call that crystal growth. Let's look at some good crystal growth. So light, moderate snow, you may see KDP around 0 to 0.2. You're not really seeing big changes. They're extremely subtle changes, or really no clear enhancement of KDP aloft. When you start to get into heavier snow, you may see some of these more are these greater enhancements in KDP, perhaps 0.2 to 0.4 degrees per kilometer in our favored growth zones. And what I've observed personally and what I've seen in some research, really heavy snowfall, when you're talking about those 2+ inch an hour rates, oftentimes you might start to see KDP values aloft that are closer to 0.4, 0.5+ degrees per kilometer in your favored growth zone. And so I highlight there, I change it over to white just to sort of grab your attention. Remember, for this, you got to look at those higher elevations on radar, because you want to look at where you would be growing your very efficient crystals in terms of giving you your higher SLRs and your higher snowfall rates. So let's look at a case from the DC radar LWX. This is from one of their big, I think it's really their last really big snowstorm, January 23rd, 2016. Looking at reflectivity here on the left, correlation coefficient on the right, lots of snow across the area, CC is nice and high. We'll now look up at 3.4 degrees. We see reflectivity here on the left and KDP here on the right. And if you were to sample this, you'd see that KDP values are all generally less than about 0.2 to 0.3 degrees per kilometer, really even lower than that. We don't really see any noteworthy enhancement of KDP aloft. So while reflectivity, you see some higher values of reflectivity in closer to the radar, KDP is telling us, well, maybe these aren't the most efficient ice crystals. Maybe they're developing at warmer temperatures. Maybe it's these clumps of denser snow crystals. KDP is saying we're not really getting a lot of dendrites and a lot of plates, a lot of the ones that are really going to give us those high snowfall rates. So let's look farther south. Let's head south towards some better ascent that was going on at the time with the Wakefield radar. And you'll notice with this, we have some bright banding going on. So they're not getting snow here, but we can use the clues aloft where the crystals are forming to give us an idea of, you know, if this is heading north, what's heading our way up in DC? If, let's say, we're providing DSS up in the Washington, DC area, for instance. Well, look down here to the south of the radar. And at 3.4 degrees, we're looking up 15, 20,000 feet. We're looking up pretty high. And so I'll highlight it there, and you'll notice this very clear enhancement in KDP values, 0.5 degrees per kilometer and higher. That enhanced KDP is signaling to us, in addition to pretty high reflectivity at some of these higher altitudes, that, yeah, we have a lot better ascent and crystal growth ongoing there. So we look at a cross-section along that line I drew, reflectivity on top, specific differential phase, KDP down on bottom. And there you can see you're up around 20,000 feet. If we were to look at a thermal profile, this would be in our favored ice crystal or dendritic generation zone. So I'll highlight it there. It's a high KDP near negative 15, negative 20 degrees Celsius. Somewhere in there, perhaps a few degrees even warmer than that. Near the ecotop, we can see a lot of ice crystals forming quickly. We know there's good ascent in there. So if that's moving north, we need to be looking out for it. And there we see all of our dendrites and little plates forming. I'm not the greatest graphic design artist. This is my rendition of a dendrite for you. So let's look at a loop now from DC of going forward in time, what we can see in terms of our snowfall observations at both BWI and at Dulles, and what happens with KDP. And you see these enhancements in KDP that start to show up. And you notice our values in our observed rates are increasing as well. So actually, I'll loop back through that again. So I'll restart the slide for you here, and you can watch it one more time and see what happens. You notice our higher values of KDP are starting to appear aloft. It was that better ascent to the south was moving in our direction, and KDP helped us see that. Our radar helped us see that. It's moving our way. If we know our thermal profile is going to support snow, we better be on the lookout for heavy snow over the next few hours as it's coming our way. And sure enough, they started to see even heavier snowfall rates with that. And they increased to about 1 to 2 inches plus per hour after 6Z. You can see how KDP helped us out there. So heavy snow identification. We give us a check mark on our lots of crystals growing aloft. We got that down. But the second thing we want to know about is aggregation. We talked about that off the top as well. That clumping. If we got lots of crystals, but then we clump them into these even fluffier, big, giant snowflakes, we can stack them up even faster. We can really enhance our snowfall rates then. So how can we see aggregation ongoing with our radar? We look once again with KLWX, reflectivity on the left, differential reflectivity on the right, and we'll notice here some higher values of ZDR. And I'll light that up for you right there. And remember, differential reflectivity, if we go from just dendrites, individual dendrites, and then we clump them together in terms of these bigger aggregates, while the shape isn't necessarily spherical, it returns back to the radar power that sort of appears spherical to the radar. The random orientation of the aggregates, the lower density as they clump together, all these things help to drive ZDR down closer to 0 dB or slightly above 0 dB. And so there's a change that ongoes here in the aggregation process. All right, this is probably the fanciest GIF I've ever produced in my life, so that's telling you my abilities again as a graphic design artist. Watch as we have our dendrites form in the cloud, and then as they grow and collect, our ZDR slowly drops. So you see this process of lowering ZDR as we get closer and closer to the ground. And aggregates, assuming your ZDR is calibrated properly, that's a whole other can of worms for another time, but assuming proper ZDR calibration, aggregates tend to give you values around 0.1, 0.2, 0.3 dB. You generally want to think close to about 0 dB. And those fluffy aggregates can enhance snowfall rates. So let's draw a cross-section, or let's look at a cross-section through this area right here where we get some of those higher ZDR values aloft. Remember, we're looking at 3.4 degrees, so our altitude above ground level or above radar level is increasing quicker than if we were looking at 0.5. So let's take a slice through there. Reflectivity on top, differential reflectivity on bottom. And sure enough, look, at the top of the cloud, or higher up in the cloud, you get these much higher values in ZDR. So what's going on? Well, you remember if we start that animation again, our dendrites form aloft. They have more horizontal component than vertical component, so they give back high ZDR. As they start to clump together, if we have favorable aggregation processes ongoing, perhaps an isothermal layer, or we're just seeing a big depth of our dendritic growth zone, it's thousands of feet deep, so we know we're going to get some aggregation in there. As they start to clump together, they send back lower ZDR, and so you get these much lower values here beneath your dendritic growth zone. Similarly, you see, well, at least in the opposite direction in terms of magnitude, you see an increase in reflectivity because instead of a bunch of small crystals, now you have these bigger snow aggregates. And because the radar cares a lot about the size of the hydrometeors you're scanning, these bigger snow aggregates send more power back to the radar than a lot of smaller individual dendrites. And so this process of aggregation, you see this increase in reflectivity towards ground, and you see higher values of ZDR aloft decreasing towards ground. So if you tie that back in with a lot of KDP aloft or some enhancement of KDP aloft, and you see this aggregation type process ongoing, you got your 2 bullet points right there for really heavy snowfall. Correlation coefficient, there's also a subtle little signature there. It's not quite as strong, but you tend to see some slightly lower gates of CC aloft where you're growing those crystals because you get the different shapes in crystals. There's some diversity to their features. And then as they aggregate into these clumps of bigger snowflakes, to the radar, they all look pretty similar suddenly. And so what that causes is an increase towards ground in terms of your CC values. So that's another sign of aggregation. So you can see all these features together, and if it's moving in your direction or it's occurring aloft, and let's say maybe you're not getting a lot of reports, or it's in an area where maybe you're trying to verify. I just got a spotter that gave me 3-inch-an-hour snowfall rates. I don't know if I believe it, but you're seeing some of these features in radar. Well, maybe you do have more confidence. Again, we're trying to boost confidence with what we see in radar, and so you can go forward from that. All right, so heavy snow identification. Check mark on the aggregation. Snowfall rates are maximized by 2 primary processes, as we just talked about. You want to see vigorous crystal growth aloft, so enhanced KDP, generally around -15 degrees Celsius, but we're talking in that range, -12, -18, in general, where you're efficiently producing your dendrites and maybe even some plate-type structures. And then you want to see aggregation as hydrometeors are dropping down towards the ground, decreasing ZDR as we go from individual crystals to those bigger clumps, and then increasing reflectivity and CC towards ground. You get those 2 together on radar, and that's a pretty clear sign that you may be dealing with some heavier snow. So our last little subset or example for you is light winter precipitation. We just went from talking about heavy snow, now we're going to talk about light winter precipitation, and we are becoming much, much more aware over the last several years of what kind of impact light winter precip can have really across the country. It catches people off guard. It may catch road crews off guard. It catches all of us off guard, and because the margins are so thin, whether it be talking about the temperature, if we're below freezing, whether it be if there's going to be precipitation or not, whether there's even just going to be mist, the margins are so thin, it's tough. It's really tough to hammer home on some of these cases, but they can be really impactful. We've seen examples all around the country. And so with dual polarization radar, we can identify it better and where the highest impact areas are. And so at least in the moment when we're providing DSS, when we're providing support for partners, we can say, yeah, radar is telling us, and combined with observations, that this certain area is actually where we're probably going to have the highest issues in terms of, let's say, roadway conditions. All right, so how do we do that? Well, let's talk about a common example that we have to deal with, something that really kind of gnaws away at us as we're trying to figure out some of these tougher cases. Low-level precip formation. Let's imagine that we're dealing with temperatures below 0 degrees Celsius throughout the atmosphere. So we're sub-freezing throughout the atmosphere, but let's imagine we have a lot of dry air aloft, a layer of dry air aloft. We have saturated air beneath it, though. So we imagine we have lots of clouds there at the top of this saturated layer. And the temp is at or maybe just below freezing, closer to the surface. let's idealize a sounding for you, and we'll look at the temperature and the dew point tracing and see what I'm talking about. And let's think we have some sort of subsidence inversion, ridging perhaps on top of this layer of saturated air, beneath this layer of dry air. We're not generating any precipitation aloft. So all of our precipitation is going to be generated in this saturated air much closer to the ground. And it's not really, really cold. We're definitely warmer than, let's say, -5 Celsius. And let's imagine even if this line were closer to our 0-degree line, we're even warmer than that. So this saturated layer, this moist layer, is only a few degrees below freezing. It's too warm to generate ice crystals. So we end up getting a lot of what we call supercooled liquid drops. And supercooled liquid drops can really be a stickler, and they cause a lot of trouble, these guys. So often what we see, that trouble, is freezing drizzle or mist. And if you've been dealing, let's say you had a pattern of cold air coming through and you're just starting to bring in some warm air aloft, but you're still sub-freezing throughout the column, and you've been dealing with temps that have been in the teens for the last week, and everything is chilled to the bone, all the surfaces around your area are, you can get some big problems with just freezing drizzle or mist, especially unexpected freezing drizzle or mist. So what can we do with radar to help us hone in on the biggest issues? Let's imagine here, or not imagine, this was a case from central Oklahoma from a year ago. It was a couple days after we had huge issues. And I know Ariel's out there listening. He could tell you all about, I'm sure, what he saw on this day from traveling around. But on the left, we have reflectivity. On the right, we have correlation coefficient. This was 2 days later, but it was another case where we had some issues in terms of our roadways. And what we have here at 0.5 degrees is extremely light echoes to the southeast of KTLX. We're talking about negative dBZs and maybe something close to 0 dBz, so very light precipitation. The reason why I show you correlation coefficient off the top is because our reflectivity is so low, we want to make sure it's a meteorological echo that we're getting back. And sure enough, we see our high CC. And so we're good to go there. And I'll highlight it and flash it for you. High CC confirms we have very light precipitation that is meteorological. And so, okay, something's going on here. And on this day, we were sub-freezing at the surface across the area. So that at least starts to raise alarm bells, at least in this case where we're looking at radar data at 1903 UTC. Differential reflectivity, it is close to 0. It's these grays and blues, all these values right around 0 dB. That ZDR close to 0 dB, first off, tells us we're getting equal contributions of power back in the horizontal and the vertical. Well, what tends to give us equal contributions back? Well, we did our homework beforehand. We saw there wasn't a lot of potential, at least initially, for ice crystal generation aloft. It looked like it was all going to be low-level processes, probably going to be tough to get ice crystals, but we're getting ZDR that is close to 0 dB. It's spherical, it's meteorological. This looks to be small drops or even droplets. This looks to be supercooled liquid water. Of course, we can know that to be freezing drizzle or freezing mist. So that, of course, in this instance right here, we know we have freezing drizzle or freezing mist ongoing. That's pretty impactful. Temps below freezing, as I mentioned, so freezing drizzle. Now, this is where it gets really neat, and you can see the differences here. Reflectivity still on the left, correlation coefficient on the right. Suddenly now we have this area of also very low reflectivity, some subtle differences in the spatial presentation of it versus to the southeast of the radar, but all in all, not too dissimilar. Correlation coefficient, we zoom in real close, and we see some lower values of CC, but that's just clutter around the metro, the Oklahoma City metro, and to the northwest. But in a lot of it, once again, we have these higher values of CC, once again confirming light precipitation there as well. So what's the difference between these two? Let's flip it over to ZDR now. And there's a very clear difference in ZDR. These values of ZDR, these yellows, even reds, 1, 2, 3 dB. What's that telling us? It's telling us there's more horizontal component than vertical component. And at this time, we had at least a subtle little disturbance coming in from the west, a subtle impulse that was at least giving us a little more saturation at colder temperatures where we can start to generate ice crystals. And so to the southeast, where we're getting low ZDR and these low-level processes, we're seeing that it's small supercooled drops. And to the northwest, ZDR is confirming to us that it's actually ice crystals. And reports at the time, very much so, were saying we had these very small flurries forming to the northwest, but we were getting freezing drizzle to the southeast. So which one is more impactful? Well, the flurries might just blow around and not really collect on anything and not cause big roadway issues. The freezing drizzle may coat on everything, and especially if you've been dealing with cold temperatures for several days or weeks, you know that freezing drizzle is going to be way more impactful than the flurries are. And so, using ZDR and confirming that we have precipitation with correlation coefficient, we perhaps can tell folks over to the east of Cleveland County, yeah, you're going to have a lot of issues with slick roadways. But then looking at radar to the northwest of Oklahoma City, we can say, well, there'll be some flurries, but it's not going to be nearly as big of an issue for road treatment or perhaps accidents. So 2 days earlier, when we had the freezing drizzle all across the metro, these were some of the things we saw. Tons of vehicle accidents all over the metro. Unfortunately, fatality collisions, several fatality collisions, all from a very, very light freezing mist and freezing drizzle event. And it catches people off guard, and it can creep up on us, and it can have just as big, if not bigger, impacts than some of our biggest winter storms, for instance, in terms of the accidents we see, and unfortunately, perhaps the casualties that we see from it, just because it can catch us off guard. So when you're in the moment and you're delivering decision support, or you're issuing a special weather statement, or thinking about an advisory, you can use the dual-pol variables to really hone in on where are the most impactful areas going to be in terms of what precipitation type you're seeing. Late winter precipitation, as we just mentioned, it may be very subtle on radar, and at first you may think, you know, the model signal, the QPS signal is nothing, but it could be really impactful if you get the wrong combination of ingredients at the surface. So you want to utilize that observational and model data to diagnose what type of precipitation type you're going to see. Are you going to see crystal formation, for instance, or is it all going to be low-level processes that give you just super cool drops? And then you want to use that dual-pol data, like we just did, to add confidence to our diagnosis and really start to drive home, okay, these 3 counties, we got big problems there right now or over the next few hours. So with that, and I apologize for our technical difficulties off the top and whatever gremlins were here at SPC, perhaps mice that were chewing through the phone line, at least, and disconnected me at first. But fortunately, Ariel was quick to contact John Hart here, and who got my attention to indicate to call back in. So I apologize for that off the top, but thank you very much for your time today, and thank you to Brian for setting this up, and Ariel initially for inviting me to do it. Once again, Joey Picca is my name. I'm a forecaster here at the SPC. There's my email address. So comments, criticisms, complaints, favorite places to go get pizza when you're in New York, let me know. What questions you got, send me an email. And right before Ariel left, he put together this huge web page. He'll put this together where we have all sorts of educational training videos present. And I have a subsection in there for dual-pol applications, including a lot of what you just saw here. So if you want to go back, minus the disconnection or the lack of connection there briefly on the phone, much more streamlined for you. You can go back and watch all those videos there, so that's available at that URL, and you can check that out. So once again, Brian, thank you so much, and I'll hand it over to you and see if there are any questions.
Thank you, Joey. Outstanding presentation. Really appreciate it. Got a bunch of ideas for building new procedures here myself.
Great.
Again, great information. As far as all the folks out there, again, it's gone a while given our early issues, but I appreciate you sticking around. Hopefully it was worth your time. If you have any questions, feel free to go ahead and raise your hand or type them in. I can go ahead and unmute your line. But now's the time if you've got any questions for Joey.
Silence from the land.
Looks like it. You must have explained everything wonderfully.
Or they've all checked out.
If nothing else, you've got Joey's information right there. As far as the Central Plains Sioux group, our next subject matter expert webinar, we are leaning toward a fire weather-based webinar getting into probably the February time frame. We're working with someone out of the Bureau of Land Management to come in and give us their insights regarding fire weather. I do see one question just popped up, actually a comment from Brian Cran. Very nice presentation. I agree 100%.
Thank you very much.
Thank you, everyone, for dialing in, and keep an eye out. We'll be sure to send out notifications for any future presentations of this nature. Thanks very much, Joey, and everyone have a great day.
Thank you so much, Brian.